Hello, everyone. Let's start this lecture by the concept of directivity, but this time for arrays. So imagine you have an array like that, and you're interested in finding its directivity. So that's one important thing to consider. And for that, I'm going to talk about the directivity of the array factor first. So, for example, you have now four patches or microstrip antenna, patch antenna, and of course it's an array in this case. So you also have an array factor. Now the question is, uh, what would be the directivity of the array factor? That's different than the directivity of the antenna arrays, because directivity of the array factor, it only depends on the array factor itself. So it does not take into account the antenna that you have. So we're going to first talk about the directivity of the array factor for two main type of array factor that we've seen in this course, which are broadside and end fire. So, and also for end fires and broadside, we are assuming that we are talking about no grating lobes right now. So now, what would be the directivity of this? So the textbook actually derives that. So the way that it's derived is that if you remember, our array factor can be expressed as sine and psi divided by 2 divided by sine psi divided by 2, where capital N is the total number of antennas and psi was kd cos theta plus beta. That's our electric phase, and that's the phase due to distance. So we know our array factor. Now we are essentially assuming that we are pretending that this is our electric field. So of course, assuming that you have an isotropic antenna, that would be multiplied by e to the power of minus jkr divided by r. So I should say we assume that this is our electric field when multiplied by e to the power of minus jkr divided by r. So we are assuming that we have some isotropic antennas, which are hypothetical. Now, if you do that, and you can check the textbook for derivation, so essentially you find radiation intensity, you find total power radiated, and then you get to the point of finding the directivity based on knowing radiation intensity and total power radiated. But the end result is important, and it shows that the maximum directivity is approximately 2n d divided by lambda. So this is our maximum directivity that we have for broadside. So this is our broadside directivity. And of course, this is dimensionless. If you want to change it into dB, you take 10 log of this number. So this is the directivity of broadside, and we can easily check it with a quick example. For example, assume that d, which is the separation between element, is lambda divided by 2 half of wavelengths, and then the number of elements are 10. So that essentially means if you have 10 isotropic antennas with the separation lambda divided by 2, and we also assume that's a linear, of course, uniform array. So if you have something like that, 10 isotropic sources with this separation, then the maximum directivity, you can find it by 2 times 10 times d divided by lambda becomes half. So it's going to be 10 dimensionless. And if you want to convert it to dB, this is a special case because that becomes 10 log 10 of this. And you know that log of 10 in base 10 is 1. So that's going to be 10. So 10 dimensionless and 10 dB. They're the same thing in this case. So that's for example, the directivity of the broadside that we have. So this is for broadside. Now, when we go to end fire, the situation is slightly different. So again, it's going to be a similar expression, but this time our maximum directivity would be 4n d divided by lambda. So you see that we actually increase the directivity by a factor of 2 compared to broadside. So this is for our end fire. For example, an end fire that has a main beam in theta equals 0 or theta equal 180. So that's your end fire in this case, and this is your broadside. Now, so this is very important to note this factor of 2 in these two cases. Now, before continuing with this, let me also mention something which can be source of confusion, and then we hopefully explain this confusion. So when you look at this, you see that for the equal number of elements and the same separation, directivity of the end fire, assuming one main lobe, is essentially more than the broadside. But then if you compare the half power beam widths, it becomes a bit confusing that half power beam widths, again, comparing the same thing, half power beam widths of the broadside would be smaller than half power beam widths of the end fire when we are comparing under the same situation. So half power beam widths of the broadside becomes smaller than half power beam widths of end fire. And this becomes confusing because if you say the directivity is more, so imagine you have an antenna with this main beam, and if you have another antenna which is more focused or more directive like that, then of course when you're comparing the half power beam widths, you would say the half power beam width of the more directive one is smaller. So this is very natural. This is, for example, the half power beam width of the broader one, and let's say this is the half power beam width of the smaller one. So you are comparing this angle with this angle. So usually when we have a more directive antenna, half power beamwidth of that would be smaller, but based on this equation, you see that the broadside is less directive, but in this case, its half power beamwidth is also smaller. And to maybe mention one more thing here is the equation that we have for directivity. If you remember, from the textbook and from the lab, the directivity can be estimated by 4 pi theta 1r theta 2r, where this is the half power beamwidth in two perpendicular planes and in terms of radians in this case. So this r is radian. So if you have a beam and you have two cuts of the beam, perpendicular cut, you get the half power beamwidths in each of them, and then you can approximate directivity. And this clearly shows that if half power beamwidth becomes smaller, directivity becomes more. So you would say, okay, directivity is more here, so its corresponding half power beamwidth should be smaller, but in this case, it's greater. So this is the type of confusion that you might have when you go through this. But then to address this things that may look like a contradiction, we need to keep this in mind that we are not comparing similar patterns in these cases. So you see, with the end fire, we are talking about a pencil beam type antenna. So the main beam is essentially in one direction. So imagine if this is an antenna array and this is end fire along, for example, theta equals 0, and assume this is z axis. So end fire along theta equals 0, that means this is your main beam. So it's going in one direction, theta equals 0. So we call this pencil beam. It goes in one direction. But imagine now you have broadside, for example. Broadside means your main beam is at theta equal 90. So you go again, theta equal 90, but then every direction theta equal is going to be a theta equal 90. So essentially theta equal 90, as we learned in the course, is the whole xy plane. So essentially the main beam of the antenna is essentially going around the antenna, is not only in this direction, is actually covering the whole xy plane when we say broadside antenna. And this is also correct when we are considering, for example, main beam as theta equal 30. So imagine this is theta equal 0, then you go theta equal 30, but theta equal 30 goes around the antenna and make a fan beam, or a cone. So you see, we are not comparing exactly two similar sizes, similar types of patterns. So with here, we are thinking about pencil beam but with this, it's more fan beam. So we are not comparing them. We are not comparing the same thing. And this is essentially the reason that we have this situation. That although end fire is more directive, but its half power beam becomes greater because the half power, the directivity of broadside is not within the end, within the pencil beam. It is essentially more distributed, and that's why it happens. So you're essentially not comparing two same things. So you need to be careful that this type of justification is when you are comparing for the same thing. We are not doing that here. And back to this equation is essentially more reliable for this type of beam, pencil beam. But when you have a fan beam, then the accuracy of that, or it becomes not applicable anymore, or the accuracy is not going to be the same. So even when you are applying this type of equation, you need to be careful that if you want to judge based on this equation, you need to think of the same type of pattern. So this is important to notice the differences between these two patterns. So remember, this is correct, and also the directivity of end fire is 2 times that. Just keep this in mind, because usually as soon as we say directivity is more, half power beamwidth is less, this is very typical to say that, but when you are applying it to the same type of antenna. So that's one discussion I wanted to have regarding the directivity. The other thing that I wanted to mention regarding directivity is essentially related to the directivity of array factor and how it relates to the directivity of the whole antenna array. So if you have an antenna array, and again, we are assuming all the elements are the same. We are considering linear uniform antenna array. So I have an antenna array. It consists of two parts: single antenna element. So this is one thing that I have. And then the other thing that I have is my array factor. So I have these two, and for array factor, at least for these two types, broadside and end fire, I know the directivity of my array factor. So this is essentially assuming that all the antennas are isotropic sources, and then I find the directivity of that. So this is the directivity of my array factor. And for single antenna element, you also know your directivity, or you can calculate it. For example, for dipole antenna, we already calculated the directivity of the dipole antenna. So you also know the directivity of your single antenna element. Now, you might be tempted to say the directivity of the antenna array is going to be equal to directivity of the single antenna element multiplied by the directivity of the array factor. But that's not the case. So this is important to note here, that if you have an antenna array, you cannot say that its directivity is equal to single antenna element times the directivity of the array factor. So I want to emphasize that this is not equal. So don't make this mistake. This is not equal. Under certain condition, for example, if your array is broadside and if your single antenna element has one main beam, you might approximate antenna array, the directivity of the antenna array approximated by single antenna element times array factor. And this is, remember, this is not equal. So for example, if you are dealing with broadside array and your single antenna element has one main beam, then you may use this approximation just as an approximation. So for example, if you want to design an antenna array, broadside antenna array with the directivity of, let's say, about 25, and then you are using some antennas, each of them, I mean, single antenna element with the directivity of 6, and then you say, okay, I want 25, then maybe if I have 4, it could do the job. 4 times 6, 24, it's close to 25. So you could start your design based on this assumption. But if you are want to calculate what is the directivity of the antenna array, this is not the proper procedure. The proper procedure would be to go to the electric field, because we know that the electric field of the array is going to be equal to electric field of the single antenna element times array factor. So this is something that we know. So this is the situation that we know. We know that E of our array is equal to single antenna element times array factor. Then based on that, we can actually find the radiation intensity as R2, 2 eta, and then we're going to have the theta component square plus our phi component square. And of course, because we are dealing with the far field, we don't have E in the R direction. Now, having U, we can also find total power radiated, which is the integration of U over sine theta d phi, which is the element of solid angle, theta from 0 to pi, phi from 0 to 2 pi. So you see, now you have that, and you have that, and then your directivity becomes 4 pi u divided by p rad. So, and these E that we have here are coming from the E of the array. So essentially, this tells us that this multiplication rule, you can apply it at the electric field level. But if you apply it at the directivity level like that, it does not hold. It may hold approximately, but this multiplication rule is essentially for, you need to apply it at the electric field level, and then from electric field level, you can go to the power level and so on and find your final directivity value. That's one thing I wanted to mention. I want to mention a couple of more things about antenna arrays, but before mentioning that, let me have a side note regarding antenna arrays, calculating the array factor in particular, and then we continue with what I wanted to mention. So you see, in all of these materials that we had so far, we assumed that our arrays are along the z-axis. So this was our assumption. And then we ended up by saying that array factor is sine n psi divided by 2, sine psi divided by 2, and then we say psi is kd cos theta plus beta. Now, the thing I want to mention here is what happens if my array is, for example, along x direction. So imagine this would be my array right now. So now it's going to be along x direction. Or what's going to happen if it's going to be along the y direction? So how does this formula change if the array is in a different direction? So you can easily find that, but one way to look at it would be from thinking that the array factor, overall expression of array factor won't change, but then you may realize why we have cos theta when the array is along the z-axis. So in fact, this cos theta is coming from the fact that it's r hat dotted with z hat. So r hat is, of course, the outward direction, and z hat is because the array is along the z-axis. So you may say, okay, if my array is along x-axis, so if my array is along x-axis, so what you expect is that this r hat dotted with z hat becomes essentially r hat dotted with x hat, which is going to become sine theta cos phi. So then your psi becomes kd. Now instead of hat, that you're going to have sine theta cos phi plus beta. This becomes your psi. Or if your array is along y, then you would say, okay, instead of this theta here, cos theta, which is r hat dotted with z hat, now this time I need r hat dotted y hat, which is sine theta sine phi. And therefore, my psi becomes kd sine theta sine phi plus beta. And then you just substitute this psi into this expression, and you have your array along x and y. So the reason I'm mentioning this is that in the exam you might get arrays in different direction. So so if it's in the z, this is the expression for psi. If it's along the x, this is the expression for psi. And if it's along the y, this is the expression for psi. So you're just changing cos theta to this sine theta cos phi and sine theta sine phi. So that's essentially what we have. And remember that in this expression, I don't have phi, because if my array is along z axis, phi means going around the array. And as if you go around the array, nothing changes. Is essentially you're looking at the same thing when you are here or here or here. But when you are along x and phi, all of a sudden you're starting having dependency on phi angle as well. Okay, let's end this lecture with an example. So let's assume that this is our coordinate. So this is x, this is our y, and this is our z. And we have 5 antennas. So here, and here, and here. And the separation between these antennas are d, and d is set to lambda divided by 2. So that's the separation between the antenna. D equal lambda divided by 2. This is along the x-axis. And the current here is assumed to be I naught. This is I naught e to the power of minus j beta. This is I naught e to the power of minus j2 beta. This is I naught e to the power of plus j beta. This is I naught e to the power of plus j2 beta. So you see that the magnitude of currents are the same. So it's uniform array. And you see that you have a progressive phase shift of beta. So it's the elements are on a line. So it's a linear uniform array, the same thing that we discussed in this course for the antenna array. So this is the situation that we have. So we have 5 elements. And let's say we want to find beta such that the maximum, the main beam is essentially at 60 degrees. So let's start with that. Now, you know that, let's maybe first write the array factor. So array factor is sine capital N psi divided by 2, sine psi divided by 2. And you know that your capital N is phi, and psi is kd cos theta plus beta. So this is your psi, which is this is the phase due to distance. This is the phase that we apply electrically to the elements. So that's the collection of these two sources of phase for us. Now, so you know everything here, and so the only thing you don't know is beta that you want to determine such that the main beam is at 60 degrees. So to get your main beam at 60 degrees, we want to have the array factor to be maximum. And remember, we want to have theta max 60 not for the array, because array only also has dipole. This theta max is only for the array factor. So we essentially want to have the maximum of array factor to happen at theta equals 60. Till now, we don't have any discussion on the particular choice of antenna. So this max refers to array factor. And we know that array factor, it can be maximum when psi is 0, for example, because if psi goes to 0, that means they're all in phase, or you can think of it as mathematically that if psi goes to 0, the limit of this AF goes to n, which is 5, and it becomes maximum. So setting psi, which is kd cos theta plus beta. We want it to happen to be 0 at theta equals 60. So you just substitute theta with 60 here. So that becomes this, we need to satisfy that. Our k is 2 pi lambda. Our d is lambda divided by 2. And then the cos of 60 is half plus beta equals 0. And therefore your beta becomes, so now lambda and lambda cancel, 2 and 2 cancel. Your beta becomes minus pi divided by 6. So that's the beta that you need to have the maximum array factor at 60 degrees. So this is something that we have. So let me double check that. D half a wavelengths, cos of 60, cos of 60 is half. So for some reason I had 1 divided by 6 here, and therefore this becomes minus pi divided by 2. So hopefully I haven't made any other mistake. It seems fine. So beta is minus 90 degrees. So this is my beta. So now I know this is my maximum array factor. And also remember that to not have grating lobes, for broadside, D should be smaller than lambda. So that's for theta equal 90 is broadside. For theta equal 0 or theta equal 180, which is the end fire, D should be smaller than lambda divided by 2. So for other angles, for example, 60, which is essentially somewhere here, it's going to be between these two, but we know that D is lambda divided by 2, so we already a smaller, we already at this point, so theta equals 60, it's expected that there would be no grating lobe. In fact, if you look at the problems of the textbook, there is a problem related to the equation for separation so that we don't have grating lobes at arbitrary angle, and instead of this lambda divided by 2 and lambda, you get to something as 1 plus magnitude or absolute value of cos theta. So if you see that if you are dealing with cos of 90, you essentially get 1 times lambda. You essentially get lambda, and if you have theta equals 0, you get 1 plus 1, 2 lambda divided by 2, and for other angles, it's going to be as you see between them. So that's so based on that, we know that there would be no grating lobe. So maybe I write theta max here, and this is absolute value because the cos can be also negative. So that's a side note here. Now this, when it's done, maybe we can add something to this, and we can, for example, say what would be our electric field, but this time total electric field at xz plane. So this is something that, let's say we want to find E total on the xz plane. So we already have our array factor, so we know that E total is essentially E single element times array factor. That's the pattern multiplication rule. So now, so we know our array factor. We have the expression. We know capital N is 5, psi is this, and we know that beta is minus pi divided by 2. So everything is determined there. So we know this. The only thing to find is the single element. So the single element is just a dipole along the x direction. So essentially, I need to solve this problem. So essentially, I need to solve this problem when you have a dipole along x direction. And I should have said in the beginning that I'm assuming these dipoles are infinitesimal dipole. If they are infinitesimal dipole, finding A is very easy. If you remember, A is of course in the direction of current x hat, and then I have mu naught 4 pi, and then I have I naught, which is the current, times the length of the antenna, I naught L, and then e to the power of minus jk r r. So this is my magnetic vector potential for this single antenna element. And because remember, because it's so tiny, infinitesimal, then I have this just as that. Otherwise, as you know from other parts of the course, you need to have a better approximation for the phase. So this is something that we have for the infinitesimal dipole, and now we need to convert that to a spherical coordinate. So to convert that to a spherical coordinate, perhaps I can do it here. So we know that AR, A theta, A phi is equal to sine theta cos phi, sine theta sine phi, cos theta, cos theta cos phi, cos theta sine phi, minus sine theta, minus sine phi, cos phi 0, then AX, AY, AZ. So this is my Cartesian on this side, a spherical on the other side, and I can remove this. Keep in mind that beta was minus 90. So I know that I don't need AR, that's not relevant in the far field. So I'm just going to use A theta, and A theta becomes cos theta cos phi times AX. And I know that AY and AZ are 0. Remember, I only have X hat. So that's my A theta. And A phi is minus sine phi AX again. And again, I don't have AY and AZ. So having that, I can find my E theta in the far field, minus j omega A theta, and E phi becomes minus j omega A phi, and I know that ER is 0. That's why I didn't need to worry about AR. ER is just simply 0. So now, I think it would have been nicer when I said find E total. I should have said find E total in the far field, because now I'm using far field equation. So let me go back here and say we want to know E total on the XZ plane in the far field. So this is my situation. But remember, also I said I want to know it on the XZ plane. So if you are on the XZ plane has two sides. This side. Now, what is the definition of XZ plane here in the spherical coordinate? Remember, this angle is phi. So when you are on the XZ like that, here phi is 0. So, and then if you go on this side of the XZ plane, here phi is equal 180. So if you are on the XZ plane, phi is either 0 or phi is 180. So based on that, you see that if phi is 0 or phi is 180, a phi is going to be 0, because sine of 0 and sine of 180 is 0. So this becomes 0. So if a phi becomes 0, therefore e phi also becomes 0. So the only thing that remains is this one. So I can just say my E theta is becoming minus j omega A theta. So minus j omega, and A theta is cos theta. And now I have cos of phi, and cos of phi, it could be cos of 0 or cos of 180. So it's going to be a plus minus here. So I'm going to have a plus minus here, plus minus 1, and then AX. So therefore, my E total becomes, E theta is of course theta hat direction, so I can just say theta hat, and then this plus minus I can bring it here, it becomes minus plus, because it's going to be multiplied by negative j omega cos theta, and then AX, which is this, mu naught 4 pi I naught L e to the power of minus jkrr, and then times my array factor, which is sine n psi divided by 2 sine psi divided by 2. So this becomes essentially my total electric field in the far field in the XZ this side and in the x-set the other side, and that's why I have two sign here. So that's essentially what's happening in this situation. So hopefully I haven't made any mistake here, and let me know if you see any mistake. So now let's change this a little bit, and this time let's do something to create grating lobes, and then focus a little bit on this grating lobes. Now imagine that we find everything as in the first part of the question. First part of the question we said we want array factor maximum to be at theta equals 60. Now based on that we found beta to be minus pi divided by 2. Now I'm saying, let's assume that, for example, the person who's fabricating this or creating this antenna make a mistake. And the mistake, the nature of the mistake is the following, that you do everything based on the assumption that D is half a wavelength. But the person who fabricates it, then the person makes a mistake, and instead of half a wavelength, the distance changes to, so maybe from half a wavelength, the distance changes to just one wavelength. So from here, you go to here. Of course, you finish your design and your beta is minus 90. Now we want to see what's going to happen with the array factor. Do we get any grating lobes? And if we do, what would be our grating lobe? So let me again remove this and go back to our array factor equation. Okay, so this is my array factor equation, sine n psi divided by 2, sine psi divided by 2. I know that my array factor becomes maximum if psi divided by 2 becomes n pi. So if psi divided by 2 becomes n pi, both numerator and denominator goes to 0, and therefore mathematically this becomes maximum. From a physical point of view, you know that if psi divided by 2 becomes n pi, is the same thing as saying psi is 2n pi, and we know that 2 pi, any multiplication of 2 pi is essentially in phase. So things are arriving in phase, and therefore you get to the maximum. So now I need to check at what angle psi becomes 2n pi. So I'm just going to write my psi, which is k, so 2 pi lambda times d. Now d becomes lambda. So this becomes now lambda. So 2 pi divided by lambda, d lambda, and then cos theta plus beta. My beta is already set to minus pi divided by 2. So I know that. So I'm looking for theta that creates main beam for me. So I need to set it to 2n pi. So you see k times d, the new d, cos theta plus beta equal 2n pi. So if that's the case, I can start canceling pi. Therefore, and lambda cancel. So I get 2 cos theta is going to be equal to 2n plus half. So 2 cos theta is 2n plus half. Therefore, cos theta becomes 2n plus half divided by 2. That would be my cos theta. Now, I start substituting for n. So let's say n is, for example, 0. If n is 0, cos of theta becomes 1 divided by 4. So of course, 1 divided by 4 is going to give me a solution. So that's definitely 1 theta there. So let's have n equal 1. So if I have n equal 1, I get 2 plus half, which is going to be 5 divided by 2 divided by 2, 5 divided by 4. So I know that there is no solution here. So I'm not going to go to plus 2. Instead, I'm going to go to negative 1. So if I go negative 1, I'm going to have minus 1 here. So that's going to give me minus 4 divided by 2 plus 1 divided by 2 minus 3 divided by 2 divided by 4. This is going to be minus 3 divided by 4. So that's what I have. That's definitely going to give me a solution. and then n equal minus 2. N equal minus 2, I'm going to get minus 4 here. That's going to be minus 8 divided by 2, and then plus 1 divided by 2, minus 7 divided by 2, minus 7 divided by 4, which is greater than 1. And that's no solution here. So as you see, I have now two solutions. One of them is cos theta 1 divided by 4. So if I solve that, I get 1 theta max here. And if I solve this one, I get another theta max here. So as you see, if you accept one of them as your main lobe, the other one would be your grating lobe. And that also makes sense because D is one wavelength and you expect to have your grating lobe. So that would be one sample example for array. So we chose beta to have a certain main beam direction just for the array factor. And then we went to E total. So we needed to calculate E of single element. So we started multiplying them. And then we also discussed one possible error that after all of this design, if you have the separation different, note that you don't get even your theta equals 60 that you started with, because theta equals 60 was designed based on separation of half wavelengths. So you start actually getting two new things here, which you need to figure out, which you need to take the a cos function to find the theta that's the max there. Okay, so that's one example for antenna arrays. Thank you.